Let me see. Okay, can you hear me?
Yeah.
Okay, so I returned the exams yesterday. You should be able to see your exam online. Let me know if there's any problems viewing it or whatever. And let's see. Over the two classes, I have this class and I have the afternoon class, which I mean we're doing the same thing, and I gave the same exam. The average was about 77. So overall, they were pretty good. I'll put solutions up this afternoon. If you have questions about the grading, just let me know. Are there any questions now? Anyone have any questions about it?
I don't see mine.
You don't see your exam?
Mine was turned in a little bit late though. This is Jason.
Oh, no, I posted it. Do you see your grade and not your exam, or neither?
I don't see either one.
Oh, I'll check it after class. I might have just skipped one, but it was graded and everything, I'm sure.
Okay.
But I'll put, if it's not there, I'll put it up right after class. I think it's easy to just skip one because of the.
Sure.
Yeah.
Thanks.
Okay. I'll check it. Okay. Other questions? Okay. So I'll continue with the lecture then. We're going over these power series solutions. I'm going to go over the example we did last time again. It's not that easy to get started with this, but okay, so we were talking about solving differential equations using power series, and you should be able to see the lecture notes now. Okay, and also we're starting part 3. So there was, I'm starting a new file, so if you want to get the notes, they'll be, I haven't put them on the Moodle page yet, but it'll be part 3 now. Okay, so we were looking at this very simple differential equation, y double prime plus y is equal to 0. And we'll put the initial conditions, I'll call the initial position A0, and the initial velocity, we'll call this A1. Okay, so the idea is that we start with the assumption that we have a power series solution. So we just write down a power series, which is going to be sum an x to the n. Remember, we take the center of this power series to be 0 because the initial conditions are at 0. So if this were not 0, but some x naught, we would take a power series at x naught. Okay, and this means that if this series converges, it will represent a function, and when we plug in x equals 0 to this function, we get a naught. And if we differentiate this power series and plug in x equals 0, we'll get a1. So that's why I'm calling the initial conditions a naught and a1, because they are going to be exactly the first two coefficients of this series. They're going to be the position at x equals 0, and they're going to be the velocity, the derivative at x equals 0. Okay. So that's what it says here, is that that's automatically going to hold. Okay, if you write down a power series like this. So then we want to plug the power series into the differential equation and get conditions on the coefficients for it to solve the equation. And those conditions for the series to solve the equation will help us generate the coefficients. That's what we need, is to determine these numbers an. So we just go through this usual thing of differentiating the series. So the series can be differentiated term by term. The first derivative is going to give you NaN x to the m minus 1. That doesn't appear in the equation. We just have the second derivative and the 0th derivative. And then if we differentiate this again, the second derivative appears in the equation. And that's the sum from 2 to infinity of n minus 1 n a n x to the n minus 2. And remember that since we're plugging this second derivative and this function into the equation, we want to be able to compare the coefficients. So we want to write all of the series in such a way that the exponents are n, because here we have an n minus 1 and there we have an n minus 2. We want them to be n. Okay, so that involves what we call shifting the index. So we call n minus 2n, that is, we add 2 to this exponent, but then we have to add 2 to all of the other n's. So if I add 2 to n here, I'll get an plus 2. If I add 2 to n, I'll get n plus 2. And if I add 2 to n minus 1, I'll get n plus 1. Okay? In this series, the lowest order of x is when n is equal to 2, we get x to the 0. So here I have to start at n equals 0. Okay? These are the same exact thing. They're just written in different ways. But this is more convenient because if we write this again together with this in an equation, we'll have the same exponent, x to the n, right? So that's an important thing to be able to do, okay? And remember, a good check when you do this is to just look at the first term. The first term here, when n is equal to 2, is going to be 1 times 2 times a2 x to the 0. So you just get 2a2 x to the 0. And when you look at the first term here, when n is equal to 0, you're going to get 2a2 x to the 0. If you make a mistake, you'll usually catch it that way. Okay, so now we rewrite our differential equation, which is y double prime plus y is equal to 0, with these two series replacing y double prime and y respectively. Okay, and that's going to look like this. Y double prime plus y is equal to 0 is equal to n plus 1 times n plus 2 an plus 2x to the n plus the sum an x to the n. Okay, so we just plugged the power series that we got into the equation. Okay. And from this, if this is equal to 0, remember we can add these two series. We'd have the exponent x to the n. The coefficient of x to the n on the right-hand side has to be 0 for all n. That means that n plus 1, n plus 2, an plus 2, plus an has to be 0 for all n. And this lets us solve for an plus 2 in terms of an. And we got this expression for an plus 2. Okay. Notice that we solve for the higher indexed coefficient in terms of the lower indexed coefficient. We could solve for an, but that's not going to help us. We want to solve for an plus 2. Okay. So an plus 2 is negative an over the product n plus 1 times n plus 2. Okay. And this lets us generate all of the coefficients for our power series, except for a0 and a1. But we can't produce a0 and a1. Those have to be given to us because those are our initial conditions. You know, the original problem, the original position was a0 and the initial derivative was a1. Okay, so we can't hope to generate those. Those are information we have to be given. But except for those two coefficients, we can generate all the equations from this. Okay, the increment is by 2 here. Here we have n, and here's n plus 2. So this means a0, if we know a0, we'll know a2. Then if we know a2, we'll know a4. Because 2 plus 2 is 4. If we know a4, we know a6 because 4 plus 2 is 6, etc. So the first coefficient a0 will generate all of the coefficients with an even index. Also, A1 is known to us. So A3, when n is equal to 1, we'll get that A3 is determined from A1. And then when we know A3, right, when we take n equals 3, we'll get A5 is determined from A3. And then once we know A5, A7 will be determined from A5. So the first coefficient with odd index, which is A1, will determine A3. That'll determine A5. A5 will determine A7. A7 will determine A9, etc. Okay? These are like, this is called the recursion relation. It's also an inductive formula. We determine the coefficients inductively. One of them produces the next one. All right, and here's the list. Here's how this goes. Again, I just copied the recursion relation here. An plus 2 is minus an over n plus 1, n plus 2. And then you should read these as two different columns. Read here and then go down. So A2, when n is equal to 0, we get A2 is equal to A2 is equal to negative A naught over 1 times 2 when n is equal to 0. Okay. And that's going to equal minus A naught over 2 factorial. A3, okay, if we put n equals 1 here, A3 will be minus A1 over 1 times 2 times 3. I put the 1 here just so it looks nicer. And that's negative A1 over 3 factorial. Okay, when n is equal to, did I write this right? When n is equal to 2 here, it should say. So A4, ignore these n's. These are not quite correct across. This should go here. A4 is negative A2 over 3 times 4, according to this, okay? But A2 was negative A naught over 2 factorial, okay? So this is going to be, if we replace A2 with negative A naught over 2 factorial, we'll get that A4 is plus A naught over 4 factorial, okay? So now we'd have A4 is this, and then when we add 2 to 4, we get 6. So this formula tells us that A6 is negative A4 over 5 times 6. And then if we use this, the previous line, we'll get that that's equal to minus A naught over 4 factorial times 5 times 6, which is 6 factorial. Okay. And similarly, A8 is going to be 8 is 6 plus 2, so it's going to be minus A6 over 7 times 8. But we found that A6 is negative A naught over 6 factorial. So this will be plus A naught over 6 factorial times 7 times 8. That's going to be A factorial. So this is the list of even coefficients. This could go on forever. You can only write finitely many of them. So I just stopped at the first 4. Okay, similarly, the coefficients with odd index, A3 is determined from A1. A3 is negative A1 over 1 times 2 times 3. Write that as negative A1 over 3 factorial. A5 is when I add 3 to 2. So I'll get minus A3 over 4 times 5. And that's going to be, using this formula, the previous formula, that's going to be plus A1 over 5 factorial. A7 is negative A5 over 6 times 7. And then using the previous formula, that's going to be negative A1 over 5 factorial times 6 times 7, which is 7 factorial, etc. Okay, so this A naught determines all the coefficients with even index according to, and going down this column. And A1 determines all the coefficients with odd index going down this column in this way. Okay, so when we put all of those back in the series, remember that sometimes people generate all of these coefficients. They don't know what to do. Just remember that an is the coefficient of x to the n. Okay, So all of these guys, all of the coefficients with even index have an A naught. Those are all going to correspond to even powers of x. Okay, so it's natural to put all of those together. You're going to get the solution, or the series for the solution is going to be y of x is going to be A naught, and then we use the coefficients, the first column here that we produced. I factored out the A naught. A naught is the coefficient of x to the 0. A2 is the coefficient of x squared. So you took out the A naught, you're going to get minus x squared over 2 factorial. A to the 4th is the coefficient of x to the 4th. That's equal to A naught over 4 factorial. The A naught is outside here. So you get x to the 4th over 4 factorial. This one is going to give you minus x to the 6th. A6 is this. So you're going to get negative x to the 6th over 6 factorial, etc. Okay. And the other coefficients, the ones with odd index, all have the A1 in front. Okay. A1 is the coefficient of x to the 1st, so you have to put that x to the 1st there. A3 is the coefficient of x cubed, so you're going to get negative x cubed over 3 factorial. So we took the x1 out. The next one was x to the 5th over 5 factorial, etc. So you get these really 2 series, but that's 1 power series. And this is just, at this point, it's formal. We don't know yet that these series actually converge. Okay, so this is all kind of just formal. We generated this series. So if the solution can be represented as a power series, this is going to be the power series. And it's really, we broke it into 2 power series. One series has this coefficient A naught, and the other has the coefficient A1. Okay, and those 2 series represent, well, those can be written in the summation form in this way. Okay, so this is just even powers. So since it's even powers, we call the index, we replace the exponent with 2n. So this is x to the 2n times over 2n factorial, the first series here. And the sign of the coefficients alternates plus, minus, and you can do this by putting -1 to the end there. Okay. The second series has just odd coefficients, and the way to write the odd numbers is 2n plus 1. 2n would be even. You're adding 1 to an even number, so you get an odd number. So this can be written as the summation -1 to the n. That's going to alternate the signs, x to the 2n plus 1 over 2n plus 1 factorial. Okay, so this is just a shorthand way to write these 2 series. Okay, and the first series is actually the Taylor series at the origin for the cosine function, whereas the second one is the Taylor series at the origin for the sine function. And those 2 series you should actually be able to recognize. But if you couldn't, you could just realize that the solutions of this differential equation, y double prime plus y is equal to 0, are the cosine and the sine functions. And if we set A1 equal to 0, okay, the solution of y double prime plus y equals 0 with y of 0 is equal to A naught and y prime of 0 equals 0, that's going to be exactly A naught cosine x. And if you do this, the reverse thing, so take the second derivative of y plus y is equal to 0, with the initial position equal to 0 and the initial velocity is equal to A1, the solution is A1 sine x. So knowing the solutions of those 2 initial value problems would be enough to deduce that this represents that function and this represents this function, the cosine function. Okay. Okay, so that's the solution of this. This is kind of what we'd expect from any second order equation which had a power series solution. We would get the solution is a sum of 2 power series one multiplied by A naught and the other multiplied by A1. Now, we should worry about the convergence of this, okay? So in general, of course, these two series are very well-known series, and if you learn this in calculus, you actually learn that those series have radius of convergence infinity. But if you're just solving some equation that you haven't seen before, you'll get these power series solutions. You have to actually show that they converge. Okay, so in this, we went over these convergent tests for power series last time. We did two different things. One thing we did was this ratio test for the coefficients. That won't work for these two series. We're going to look at the first series here, this one. We can't just test the convergence using the coefficients of the series, because this series has infinitely many terms which are zero. In this first series, the coefficient of x to the first, x to the third, x to the fifth, x to the seventh, those are all zero in this series. We're going to test just the convergence of that series. Okay, so what we do is we said we plugged in a number x, okay, to the series, and then we just treated this like it's a series of numbers. Okay, so it'll look like that. We're going to look at, just imagine you plug in an x equals 5 or something. That'll just be a series of numbers, Cn. Okay, and then you can look at the ratio test for series of numbers. So the ratio test says if you take this quotient, Cn plus 1 over Cn in absolute value, and then you take the limit as n goes to infinity, that will converge, the series will converge as long as the limit of this is less than 1. Okay, when we plug in what Cn is, so Cn plus 1, we increment the exponents here and the denominator, the n there, by 1. We'll get x to the power 2 times n plus 1 over 2 times n plus 1 factorial, because I changed n to n plus 1. We divide it by this, okay? I left out the -1 to the n because we took absolute values here. And that simplifies. We could flip this over and rewrite it. You have x to the 2n plus 2 divided by x to the 2n is just x squared. And the coefficients, all these factorials, if you take 2n factorial over 2 times n plus 1 factorial, the factor 2n factorial will vanish, and you'll just get the last two factors in this, which are 2n plus 1 times 2n plus 2. Okay, is this clear going from here to here? If anybody wants to explain more, I can write it out. Is it okay?
Yeah, that makes sense.
Okay, so no matter what x is, this is going to go to 0. The numerator doesn't depend on n, and the denominator is blowing up like n squared. It's 4n squared is the dominant term in the denominator. So this is going to go to 0 for any x, right? So the important thing is not so much that it go to 0, is that the limit is less than 1. It's 0. 0 is less than 1. Okay, so that says that this series is going to converge for any value of x. Okay, so since it converges for any value of x, the radius of convergence is infinity. Okay, converges for every value of x. So you can take any value. So the radius of convergence at the origin is plus infinity. Okay, it converges everywhere. Any questions? Okay, so that's how you would handle the convergence of that series. Okay, and there's a trick here. You could do the following. So we had our, so the other series, it says it could be handled similarly, but there's an easier way to do it. So we had these two series, which are the solutions. We just showed the first series converges. Okay, this is the series for the cosine function, right? Okay, And if you differentiate this series, you get minus that series, okay? So differentiating, if you differentiate this is the power series for cosine, you'll get this, you'll get essentially this series with a minus sign, okay? And remember that we said in last time, we said that if you take a power series and if you differentiate it, you can, well, the function that's represented by a convergent power series is differentiable. Its derivative is represented by the derivative of the original power series, the second derivative, etc. And these all have the same radius of convergence, okay, as the original power series. So the original power series is an x minus x naught to the n. And when you differentiate it, you get a power series that has the same radius of convergence. So the fact that in this example, where was it? The second series is essentially the derivative of the first series. It's minus the derivative of the first series. That could show you that the radius of convergence of this is the same as the radius of convergence of this. And the radius of convergence of this we just saw was infinity. So that would mean that this series has radius of convergence infinity also. But that's just particular to this example. Okay, so that's a good example, but the problem with it is we kind of know the solution to begin with. We knew that the solution of this equation would be given by cosines and sines. Okay, so very simple example. So now we'll do another example, which is a little bit more challenging. Okay, this is called Airy's equation. Airy was he was an astronomer. This equation has something to do with optics. Okay, and it's the equation, the second derivative of y minus xy is equal to 0. And again, we'll take the initial conditions to be at 0, at x naught equals 0. Okay, and this presents, this is going to look different. A lot of the, well, a lot of different things can happen when you work with power series. They don't all kind of work out the same way. Okay, so the big difference here is that you have a variable coefficient. So y is a function of x, and the x is actually a coefficient in the equation. So that changes things somewhat. Okay, so we start out the same way. In fact, you can use these calculations over and over again. In different examples, you should learn how to do this, but considering that you're just doing the same thing over and over again, you can just copy these calculations for derivatives when you have a different problem. Okay, so the function we're going to write is an x to the n. The second derivative appears same as before. We take the first derivative, just differentiate the terms in the series term-wise. So we get nan x to the n minus 1. The second derivative is n minus 1 n an x to the n minus 2. And we shift the index the same as before. Okay, so this is the same step. We added 2 to all of the n's, and it changed in this way. And we started the summation at 0. So the first term here is the same as the first term there. This looks exactly what we did in the previous example. The difference is that we have xy here instead of y. So xy, if this is our series and we multiply it through by x, we can just multiply x to the n by x, and we'll get x to the n plus 1 instead of x to the n. Okay, so all I did was multiply this through by x, and we have to shift the index of this now because this has an exponent n plus 1. We want it to be n, so we basically subtract 1 from this, subtract 1 from all the n's. Okay. And again, we should check when n is equal to 0, we got a naught x to the first here. And when n is equal to 1, we'll get a naught x to the first here. Okay, so this is xy. We're going to represent it that way. And then we just take these two expressions and plug those into the equation. And we get this. So we get, this was our series for xy, and this was our series for the second derivative. Okay. And it's pretty straightforward. Okay, so we just get, I just want to think about something here. That's okay. Okay, so we get this recursion relation. So the coefficient, so we get m plus 1, m plus 2, am plus 2 minus am minus 1 is equal to 0. And we just solve that for am plus 2. So just take the coefficient here minus the coefficient here, am minus 1 is equal to 0. And then just rearrange and solve for am plus 2. Everybody see how this gave us this recursion relation? So just ignore the x to the, like, look at the coefficient of x to the n on both sides of the equation. This is on this side, it's 0. You'll get m plus 1, m plus 2, am plus 2 minus am minus 1 is equal to 0. Solve that for am plus 2 and you'll get this. Okay. This is different than the previous one because the increment in the exponent is by 3, because the difference between n plus 2 and n minus 1 is 3. In the previous problem, we had am plus 2 is equal to an over n plus 1, n plus 2. But now it's n minus 1. Okay? And that can be confusing. Okay. So the idea is to do the same type of thing that we did in the previous example. Okay, so starting with a naught is going to be when n is equal to 1. Okay, so if we plug in n equals 1, we'll get a3 is equal to a naught over 1 plus 1 times 1 plus 2. So we get a3 is equal to a naught over 2 times 3. Okay, from this recursion relation. It's just confusing because you have to remember a naught and a1 are given. You have to generate the coefficients from a naught and a1. So you think, I'll get a naught here when n is equal to 1. Okay, and then once we know a3, we should take n equals 4 so that we get a3 here. Okay, so when n is equal to 4, we'll get a 4 plus 2 is 6 is going to be a3 over 4 plus 1 is 5, 4 plus 2 is 6. Okay, so we get a6 is a3 over 5 times 6. But we know a3 is a naught over 2 times 3. So we can replace a3 here with a3 there, and we'll get a naught over 2 times 3 times 5 times 6. And that's going to be the coefficient a6. Okay, so now when n is equal, we want this to be a6, so we take n equals 7. All right, so when we take n equals 7, we'll get a9 is a6 over 8 times 9. Okay, a9 is a6 over 8 times 9. And then we use the previous equation, which was that a6 is a naught over 2 times 3 times 5 times 6. So a9 is a naught over 2 times 3 times 5 times 6 times 8 times 9. Okay, and we just want to generate maybe some of the coefficients. This would go on forever, so we can only write a few of them down. But you should write it down enough so that you can see what the pattern is going to be. Okay, so if you had to write down more, you wouldn't have to keep coming back to here. You kind of guess what's going to happen. Okay. Okay, So those are the coefficients that are generated from A naught. Okay, all of these will have an A naught in them, right? They will have the factor A naught. Then there's the other coefficients that are generated from A1. So to get A1 here, we should take n equals 2, okay? And we'll get A4 is A1 over 3 times 4, like this, okay, when n is equal to 2. Then we increment by 3, go up to 5, okay? And because we want this to be A2, A4, okay? So 5 minus 1 is 4. So A7, wait, what am I doing? This should be a 4, right, 5. So A7 is going to be A4 over 6 times 7. Okay. Just what we have there. A7 is A4 over 6 times 7. And then use the previous formula that A4 is A1 over 3 times 4. And so you get A1 is 3 times 4 times 6 times 7. Okay, and then we'll do one more, is that we know A7, so we should take n to be 8, so that we get A7 here, and that's going to give us A10 is A7 over 9 times 10. And then we use the previous formula for A7, and we get A10 is A1 over 3 times 4, 6 times 7, 9 times 10. Then we go and we plug everything back into the power series. We should get 2 power series. One has the factor A naught, the other has the factor A1. And when we do that, it'll look like this. Remember, again, when you want to put these back in the power series, you just remember that AN is the coefficient of x to the n. That's the important thing to remember. And when you plug those in, you get these 2 series that look like this, okay? And you can kind of guess what the next term is going to be. So you get one power series that has the factor A naught, the other power series that has the factor A1, okay? And you have to prove the convergence of these 2 series. And like it says there, that'll be a homework problem, is to prove the convergence of at least one of these series. But those would be those actually have infinite radius of convergence. And the proof is not so different than the proof of the series that we did, that the proof that the radius of convergence is infinity looks kind of like the other example that we did. Any questions? Okay, so once you prove the convergence, it's very easy to see that the function represented by this series and the function represented by that series, those are going to be 2 distinct solutions of the differential equation, the homogeneous equation, which is Airy's equation. And what's more, they're going to be a fundamental set of solutions, because this is going to have, at 0, this function has, let me just write this down. Okay, so we have these, just going to write, yeah. So we have these 2 series. We have y1 of x. So this was the one that was multiplied by A naught, was 1 plus x cubed over 2 times 3. Notice you don't want to multiply this out because that's going to obscure what the pattern is. So that was one solution. Okay, and the other one looked like y2 of x was x plus x to the 4th over 3 times 4. Okay. And these are both separately solutions of the differential equation, because this would solve the differential equation y1 double prime minus xy1 is equal to 0, if you took y of 0 is equal to 1, and y prime of 0 is equal to 0. Okay, so i.e. if you took a naught equals 1 and a1 equals 0, you'll get this function, right? And if you took this one will satisfy y2 double prime minus xy2 is equal to 0, with y2 at 0 equals 0, and y2 prime at 0 is equal to 1. Okay, this means we're going to take here a naught equals 0 and a1 equals 1. Okay, so these are separately solutions. And these things tell us that we have a fundamental set of solutions. So y1, y2 would be a fundamental set of solutions. Because the Wronskian at 0 is not equal to 0. W at 0 is y1, y2 prime minus y1 prime, y2. Okay, and that's going to be from here, we'll get 1 times 1 minus 0 times 0. Which is what? Not equal to 0. Okay, so the two series that we get actually represent functions which form a fundamental set of solutions for the differential equation. Any questions? All right. And again, this is kind of useful. I mean, in real life, you get important equations which don't have solutions that you're going to be able to find by these other methods because, I mean, they're just not representable. For example, these functions here define, these solutions define functions that people give names to, but they can't be expressed using the functions that you know, like trigonometric functions or exponential functions. They have kind of interesting behavior. So, and let's just go into some of the theory about this. So this is just another example. We'd still have to show the convergence of these two series to really be convinced that they represent solutions. And so we'd like to know in advance that the equation would have a solution, a series solution. And this is just some of the theory behind this. We'll go over this rather quickly. So the first thing we need is the idea of an analytic function. So a function f of x on an interval, I call the interval I, is called analytic if for every point x naught in the interval, there's a smaller interval. Just think of this h as being a distance around x naught. So there's an h bigger than 0 and a power series, which is a power series centered at x naught. So for every x naught, there's a power series such that that power series converges to the function on an interval centered at x naught. There's a parenthesis missing there. Okay, so every function that can locally be represented by a power series is called an analytic function. Okay, and since the power series is infinitely differentiable, such a function must be infinitely differentiable. It must have all its derivatives. Okay, but that's really that's not enough. It needs more than that, but that's a consequence of the function being analytic, is that it has all its derivatives. And examples of analytic functions are the exponential, the cosine function, the sine function, polynomials. You could take rational functions, which are quotients of polynomials, and those are analytic as long as the denominator is not equal to 0. So for example, x over 1 minus x is analytic as long as you get rid of the point 1 where it's undefined. Okay. So the theorem is that if you have a differential equation, a second order linear differential equation, and if P of x and Q of x are analytic functions, oh, what did I write here? No. Oh, I forgot the derivative. So this is as usual, y double prime plus P of x y prime plus Q of x y. So the derivative is missing here. Okay. So if P of x and Q of x are analytic functions on an open interval containing x naught, then this equation would have a solution. It would have a power series solution, an x minus x naught to the n. A lot of typos here. I'll fix them right after class. It would have a power series solution, which is a sum of one power series times a naught plus another power series times a1. Okay. And these series would converge in some interval centered at x naught. Okay. So such a series, as long as the coefficients, remember this is a y prime, the coefficients would have to be analytic functions. Those are functions which are locally representable as power series. Okay. So for example, if you took y double prime plus cosine xy prime plus e to the xy, that would have a solution which is representable as a power series. Okay. And maybe to finish, we won't get through this. This is a long example, but we'll look at what's called the Legendre equation. This is a rather important differential equation. It's really a whole list of differential equations that are used a lot, especially in studying vibrations in three-dimensional space. Or let's see, they're used a lot in nuclear physics and in nuclear engineering also. And this is the differential equation y minus x squared. I use the independent variable f here. Y minus x squared f double prime of x minus 2x f prime of x plus alpha times alpha plus 1 f of x is equal to 0. So here alpha is a parameter, and it's usually taken to be an integer, 0, 1, 2, etc. So for each alpha, you'd have a different equation. And we saw one example of this in the homework, in a homework problem where alpha was equal to 1. Okay, so we'll just get a start on this. We have about 3 minutes, but maybe we won't get a start on it. We'll just, what you would do is just compute the derivatives and compute everything, every term in this series as a power series. For the second derivative, you actually have two series. You have the series for f double prime, and you have to have a separate series for minus x squared f double prime. And that's what's done here. But we don't really have time to do this today. So I think I'll stop here. Are there any questions? Any questions? Okay, so take a look at the comments on the exam, and I'll post solutions right after class, and I'll look at Jason's exam, why that wasn't uploaded. Okay, questions? Okay, and there's homework due this afternoon. So yeah, that's on the assignment page. I told you about that last week.
Thank you.
Yeah, welcome.